Hello everyone, I am Harika Shinde from Institute of Aeronautical Engineering and I am from Computer Science and Engineering branch. Today I am here to share and present my AAT Tech Talk video of a course operating system. My topic is achieving scalability in real-time system. Let's begin. Most embedded computing systems, including cell phones, wearable computers, cameras, sensor networks, portable multimedia players, GPS-based navigation devices, video game consoles, and smart homes, are powered by batteries. If energy consumption is a critical aspect of this system, directly affecting both performance and lifetime. Unfortunately, high performance and a long battery life are conflicting objectives. To achieve high performance, the system must operate at a high speed, which consumes more power, whereas achieving a long battery life requires the system to consume less energy, which means operating at a low power. At high level strategy can exploit the dependency depending on current application needs. For example, the system can degrade performance to achieve longer battery duration, or it can increase performance at the expense of a higher energy consumption. In the presence of timing and resource constraints, however, a real-time system performance does not always improve as a processor speed increases. Similarly, when reducing processor speed, the delivered service quality might not always degrade as expected. The speed performance trade off anomalies sidebar explains this dilemma in more detail. Although many researchers have looked at reducing energy consumption of real time applications, the problem of scaling performance with the speed variations requires further exploration. A proposed computational model varies task response times continuously with the processor speed, enabling the system to predictably scale its performance during voltage changes. This model implements two key mechanisms at a kernel level. Non-blocking communication buffers prevent the scheduling anomalies caused by speed variations and allow data exchange among periodic tasks with a non-harmonic period relation. To cope with permanent overloads caused by speed reductions on elastic task scheduling approach automatically adjusts task rates based on a set of coefficients which the developer can assign during the design phase based on the task importance. To simplify, comparisons of task schedules executed at a different clock frequencies within a range of f minimum and f max, all quantities of interest such as computational time and utilization are expressed as a function of speed, defined as a normalized frequency f equals to m by f max, that is frequency by maximum frequency. Thus, the validity range for normalized speed is s minimum or s max, where s minimum is equals to f frequency minimum divided by maximum frequency and S max is equals to 1. In addition, for clarity, task execution times are considered to be inversely proportional to processor speeds. They are thus modeled as Ci of S equals to Ci of 1 by S, where Ci of 1 is the task execution time at the maximum processor speed. However, the proposed solution do not depend on that condition and apply to different execution time models. Finally, in all scheduling illustration, the vertical axis represents processor speeds. Real-time task scheduling problems. Several problems can occur when a real-time application runs on a variable speed processor. When tasks share access to mutually exclusive resource or execute in a non-preemptive fashion, response times can actually increase when the processor runs at a higher speed. In addition, decreasing speed can cause a permanent overload that degrades system performance. Such problems, if not properly handled, make it impossible to control a real-time system performance as a function of the voltage and limit the use of a real-time scheduling algorithms for a resource optimization. Here it is a figure 1 representing the task scheduling anomaly in the presence of resource constraints. Task T1 meet its deadline when the processor is executing at a certain speed as well, but misses its deadline when the speed is double. Here it is a figure. Next, here it is a task 2 scheduling anomaly in the presence of non-preemptive task. Here, the task T1 meets its deadline when the processor is executing at a speed S1. Non-preemptive task. Figure 2 illustrates anomalous behavior occurring in the set of three real-time tasks T1, T2, and T3 running in non-preemptive mode. Tasks are assigned a fixed priority proportional to their relative deadline. Thus, T1 is a task with the highest priority and T3 is a task with the lowest priority. As the figure 2 shows, when tasks are executed at a speed S1, T1 has a computation time C1 is equals to 2 and completes at a time T is equals to 6. However, if the same task set is executed at a speed S2 is equals to 2S1, task T1 misses its deadline as figure 2 shows. This happens because when T1 arrives, T3 has already started its execution and cannot be preempted. A set of non-preemptive tasks can be considered as a special case of a set of tasks sharing a single mutually exclusive resource for their entire execution. Each task executes as if it were inside a long critical section with a length equal to task computation time. Once a task starts executing, it behaves as if it were locking a common semaphore, thus preventing the processor from executing all other tasks. Here it is a figure 3 showing the effects of a permanent overload due to a processor speed reduction. In the case B, the processing is running at a half speed. Now, permanent overload. Figure 3 shows the negative effects of a permanent overload condition caused by speed reduction in a set of periodic tasks T1, T2, and T3. Figure 3 shows the feasible schedule produced by the rate monotonic RM algorithm 7 when the processor runs at a given speed as well, where the tasks have computation times C1 equals to 2, C2 is equals to 2, and C3 is equals to 4 respectively. Figure 3b shows the schedule that the RM obtains when the processor speed is S2 is equals to S1 by 2 such that all computation times are double. In this case, a speed reduction generator a permanent overload that causes task T2 to miss its deadline and prevents task T3 from executing. Note that a scheduling algorithm based on absolute deadlines, such as earliest deadline, first EDF, would not prevent T3. Task T3 from executing would react to overloads by delaying all task executions more evenly. Previous work compared RM and EDF, that is, earliest deadline first, in detail for different scenarios. Avoiding shared resource blocking. Cyclical asynchronous buffers prevent scheduling anomalies due to speed variations and allow data exchange among periodic tasks with non-harmonic period relations. CABs are a kind of wait-free mechanism that let tasks perform read and write operations simultaneously via memory duplications. If a task TW wants to write a new message into a cab while a task TR is reading the current message, the system creates a new buffer so that the TW can write its message without interfering with the TR. As TW finishes writing its message, become the most recent one in the CAB. To avoid blocking, the number of buffers that a cab must handle must equal to the number of tasks that a cab plus 1. To insert a message in a cab, a task must first reserve a buffer from the cab memory space, then copy the message into the buffer, and finally put the buffer into a cab structure, where it becomes most recent message. It is accomplished as a follow. Buffer pointer is assigned to reserve cab ID. Copy message in buffer pointer, put M's buffer pointer, cab ID. Similarly, to retrieve a message from a cab, a task must get the pointer to the most recent message, use the data, and then release the pointer. The following code executes this action. Mutually exclusive resource and a non-preemptive code can generate scheduling anomalies in a processor with a dynamic voltage scaling, causing tasks to increase their response time when the processor runs at a higher speed. Even worse, decreasing the speed can cause a permanent overload that degrades system performance in an uncontrolled fashion. Such problems can be efficiently handled through a set of kernel mechanisms, including cyclic asynchronous buffer and elastic scheduling that let system designers scale the performance of real-time applications such as a function of processor speed. As successfully done in the Shark kernel, the both CABs and elastic scheduling can be easily implemented on the top of any real-time operating system as a middleware layer, and they should be included with the current standards to develop embedded system with the real-time and energy requirements. Thank you. This was my AAT TikTok video of a course operating systems.